Wind energy is the main component of the laboratory's renewables portfolio, including the economics of wind energy projects and the use of computational fluid dynamics to address both basic and applied engineering. In the laboratory, we have developed an integrated risk management tool that allows an investor, developer, or financer to evaluate the financial benefits of wind energy projects. Using this tool, the land of Iowa has been mapped in terms of financial parameters, including return on investment, net present value, and benefit to cost ratio. Iowa is a challenging test case for our tool, as the U.S. is the world's fastest growing wind energy market, and Iowa is among the largest in terms of wind capacity. Starting from the wind resource across Iowa, the tool evaluates the infrastructure, such as the power grid shown here, and determines the economics of wind energy projects. This can be seen in the close-up view of 500 square kilometers in northeast Iowa. The return on investment of wind energy projects is determined at a spatial resolution of 1 square kilometer. In addition to the wind resource, project areas include both natural and anthropological constraints with the necessary setback distances. Thus, wind energy projects identified using the tool respect the presence of wetlands, protected areas, and forests, and do not conflict with populated areas, roads, and transmission lines. In order to assure that the potential project is of sufficient size, a minimum area is easily specified. Therefore, our tool allows the investor, developer, or financer to distill complex engineering factors into an evaluation of the economics of the wind energy project over its lifetime. For a successful wind energy project, the wind must be assessed. This assessment is increasingly challenging as future projects will be sited in complex terrain, and developers demand more rapid assessments of the wind-generated electricity. Using the Swiss Alpine wind turbine test site that is located in the Alps more than 2 kilometers above sea level, we are developing sophisticated tools to accurately simulate the wind flow in complex terrain. This reduces the development time of wind energy projects. Different layouts of wind turbines can be simulated so that developers can identify the optimal locations that meet their business models. To validate the simulation tool, the laboratory is performing measurements of wind speed and turbulence on full-scale wind turbines. The measurements are a challenge, as modern wind turbines are large with rotor diameters of up to 100 meters. Therefore, a novel approach using a flying drone, which is equipped with specially developed precision sensors, is used to measure wind speeds and turbulence field. After programming the desired flight plan into a ground control station, the instrumented drone uses GPS information to fly autonomously around the wind turbine. Onboard sensors control the speed and altitude of the drone, and it can be flown in a controlled pattern. Measurement, flight, and navigation data are stored on board the aircraft, and also are simultaneously monitored on the ground station. On completion of the autonomous flight, the flying drone is landed and the data are retrieved. The measurements in the field are complemented by performance and detailed flow field measurements in our subscale model wind turbine facility. Using a 40-meter-long water towing tank, the flow over modern full-scale wind turbines can be accurately simulated on subscale models. If you are looking for a strategic university partner in the sustainable energy sector, please contact us.